Hello everyone. So today we're going to continue on 2.2. So last week we talked about on last video was a concept called K-plane. So K-plane is basically a parametric representation of a geometrical object that's similar to a plane in R2 but in high dimension, and also itself in high dimension also. So a K-plane basically have the same exact equation just like a regular plane, but a plane has two direction vector, while K-plane would have k-dimensional direction vector. So today we're going to start with a very special K-plane. So if a K-plane has one less direction vector, then the dimension it is in. Then it is referred to as a hyperplane. So, example, a one plane, or technically a line, is a hyperplane in R2. However, note one plane, or once again a line, is not a hyperplane in R3 or higher. Only in R2 would it consider to be a hyperplane for one plane. Now, using the same exact concept, you can see that a two-plane, which is basically just what we refer to usually as a regular plane, is a hyperplane in R3. Similarly, a two-plane is not a hyperplane in R4 or higher. Therefore, in general, once again, is noted the pattern involved. So a two-plane is a hyperplane in R3. The reason why it is because the number 2 is 1 less than 3. That's why it's called a hyperplane. A one plane is a hyperplane R2 because 1 is 1 less than 2. So in general, a n-1 plane in Rn is referred to as a hyperplane. Now, some of you might notice that relationship between the K-plane and the dimension is in, which is in this case always one less. So what's special about a hyperplane? A hyperplane has a unique perpendicular vector. In the dimension that's in. And therefore, a hyperplane can be represented using standard form. As a matter of fact, a hyperplane is the only plane that can be represented using standard form in whatever dimension is in. And of course, if you put one and one together and figure it out, then you should notice this is the important concept I want to show you. Any linear equation represent a hyperplane. Meaning all the linear system that we're doing, we are actually looking for intersection between hyperplanes of whatever dimension that we're in. So if you think about it, it makes sense. If you have a system of two equations in two variables, Because in two variables, we know it's in R2, and both of the equation would then represent lines. And remember, a line in R2 is a hyperplane in R2. And then when we try to look at the system of three variables, then we have linear equation. Then those linear equations all represent plane. And remember, a plane is a hyperplane in R3. And so we're looking for intersection of that. So very important to understand is that any linear equation that we have is actually an equation of a hyperplane. And when we're solving a linear system, we're actually looking for the intersection between hyperplanes. Now, show you a simple example of why all linear equation must be a hyperplane. So here's an example to illustrate. And you should realize that the concept is exactly the same and apply to higher dimension or different equation. Let's say we're given this equation right here. x1 minus 2x2 plus x3 plus 5x4 equal to 7. Okay? Very simple problem. I want you to rewrite it. And I'm going to define that different this equation in R4 so that we know there's no extra variable that have zero coefficient in front. What I want to do is to show that this linear equation is a three planes in R4. Therefore, it is a hyperplane. Oops. In R4. So how do I do that? Well, actually pretty simple. If I look at this equation right here, it have four variables here. x1, x2, x3, and x4. In order to put it in parametric representation, what I'm going to do is the following. If you think about it, it's basically this simple concept right here. Because I only have one equation, therefore I can only have one leading variable, which would be the first variable I see in my equation. Because in this scenario right here, in this equation, there is a leading entry, which is the first non-zero number in this one row matrix. And if you remember what I told you, then that would imply that these three variables are all non-leading variable. And what do we do with non-leading variables? They become the parameters. So, how do we solve our problem? Pretty simple. If you remember the process, notice the same exact process that we have done before. I'm going to solve for x1. And then, I'm going to set my parameter. I'm going to let x2 equal to the parameter t1, x3 equal to parameter t2, x4 equal to parameter t3. Now I'm ready to set up my parametric representation. x1 is equal to 2t1. Instead of minus t2, I'm going to say plus negative 1 t2. Instead of minus 5t3, I'm going to say plus negative 5 t3 plus 7. What is x2? x2 is t1. x3 is t2. x4 is t3. Now I'm going to fill in all the missing stuff. There's a 1 in front. There's 0. This is 0. Plus, plus, plus. 0 t2. 1 t2. 0 t2. Plus, plus, plus. 0 t3. 0 t3. 1 t3. Plus 0, plus 0, plus 0. Now I fill in all the missing information. Now I'm ready to put it together. This is what my vector x is. My vector x in this case is x1, x2, x3, x4, and that's equal to t1, 2, 1, 0, 0, plus -1, 0, 1, 0, t2, I forgot, plus t3, multiplied by -5, 0, 0, 1, plus 7, 0, 0, 0. That becomes my parametric form. Notice that it has 3 direction vectors. These are the direction vectors. These are my parameters. What is this last one right here? This is our position vector. And since we have 3 parameters, 3 direction vectors, this is a 3-plane, which basically means that it's a hyperplane in R4. Notice, sometimes you don't realize and don't understand. If I look at this parametric representation right here, notice that I have all the vectors that you see are vectors in R4. That is the reason why I know this object that we're describing exists in R4. And because there are 3 direction vectors, therefore it must be a 3-dimensional object in R4. And this 3-dimensional object is called 3-plane. Okay? Now, next thing I want to show you is this. Next thing I want to show you is a very important theorem. But before we actually can get to the theorems, I do want to show you something else. Imagine the following. So, give you this system right here. Let's say given this system already in most reduced form. Okay? I'm going to ask you to pause the video and try to finish the problem yourself, meaning write out the solution for yourself. But before you do that, how about look at this? This matrix is already in most reduced form. Why? Because they have 2 leading entries, and both column, which is the first and the third, have only zeros in it. All right? And because they have 2 leading entries right here and right here, therefore indicate that it has 2 non-leading entries, implying that we're going to have 2 perimeters. So therefore, we can expect the solution to this system right here is going to be a 2 planes. So what I'm going to ask you to do is pause the video and try to write out this solution that is a 2-plane. And then once you finish, unpause the video to see the rest of the video. Okay, so go for it. If you do it correctly, this is what our solution is. Vector x is equal to t1, 2, 1, 0, 0, plus t2, -1, 0, 1, 1, plus -2, 0, 1, 0. So this is my 2 planes that represent the solution. Here's something interesting I want to show you. Students sometimes don't understand how this solution works. So what does it mean is this. This expression right here allows you to generate any solution to this system. Okay? Now, what does it mean by that? Meaning that if you randomly pick a value for T1 and a value for T2 and plug it into this expression to form a vector, in this case a vector in R4, and when you multiply that vector in R4 by plugging in that vector in here and multiply by this matrix right here, the coefficient matrix, you should get -2, 1. So how about we give it a try? So let's just say we pick two random numbers for T1 and T2. Now, it's really completely random. Up to you what you pick. But because I'm making a video and I cannot ask you what you want to pick, so I'm going to just pick it for us to try. But you definitely feel free to pick a completely different number for yourself and try it out and see how that works, okay? So I'm going to just randomly pick two numbers. So I'm just going to pick, I don't know, how about T1 is 1 and T2 is 2. So very simple. So suppose I have that, then therefore they tell me that vector x would equal to 2, 1, 0, 0 plus 2 times negative 1, 0, 1, 1 plus negative 2, 0, 1, 0. And so what do I have here? Will be 2 minus 2 minus 2, that will be negative 2. 1 plus 0, which is 1. Okay. 0 plus 2 plus 1, that will be 3. And then 0 plus 2 plus 0, that will be 2. So I have this vector right here. So now what I'm going to do is I'm going to go and try to multiply that by the matrix. And hopefully what I get would be 2, 1. So let's see. So therefore this would be the dot product between 1, negative 2, 0, 1 with negative 2, 1, 3, 2. That's my first number. Second number will be 0, 0, 1, negative 1. Dot product, negative 2, 1, 3, 2. So let's see. So that would be negative 2 plus 2. I'm sorry, negative 2 minus 2. Plus 0 plus 2. And voila! That come out to be negative 2, which is good. Bottom number will be 0 plus 0 plus 3 minus 2, which is 1. Notice that is the same exact thing. So that's basically how this expression works. It's allow you to generate any solution that you want using any T1 and T2 value. And the interesting thing about it is that all the value that you're going to use for T1 and T2, if you plug it into this expression to form the vector x, which become a point in R4, all of them actually will form or stuck together and form some kind of plane. Just like a regular plane in R3, but this one exists in R4. And that's why it's called two-plane. Now, some of you, whether it's being clever or being lazy, I'm not going to judge, might choose to use T1 to be 0 and T2 to be 0. And if that is the case, notice that you just have vector x simply just equal to this vector. Because both of the direction vectors just go to 0. And now, does that mean that this vector will work? As a matter of fact, let's find out. So therefore will be negative 2 plus 0 plus 0 plus 0. And on the bottom would be 0 plus 0 plus 1 plus 0. So therefore it does work. It comes out to be negative 2, 1. So as a matter of fact, interesting thing to note, when you have a solution of a linear system in a k-plane format, the position vector always satisfy the equation, the system itself. So something we're writing down for a linear system. If the solution set is a k-plane, then the direction vector, the position vector, which we often refer to as vector v, will satisfy the linear system just by itself. It doesn't have to do anything. Okay? Now, if you think about it, it makes sense because the position vector must exist on this two plane, and everything on this two plane would satisfy the equation. Now, here's a much more interesting question. in order to describe a k-plane, not only we need the direct position vector, which we already established, the position vector will satisfy a system, a linear system, and give us the correct output. What about the direction vector? So what I'm going to ask you to do is the following. I'm going to ask you to go ahead and take the two direction vector, 2, 1, 0, and negative 1, 0, 1, 1. I'm going to ask you to plug it into this system. Oops, sorry. This system right here. And see, does it come out to be negative 2, 1? Or does it come out to be something else? Okay? So I'm going to ask you to go ahead and do that. Take the first direction vector 2, 1, 0 and do that. And then after that, note what the answer is. And then try the second direction vector, negative 1, 0, 1, 1. And hopefully the answer does not surprise you. Okay? So once again, I want you to do that first. And then pause the video, do that. And then unpause the video after you're done so that you can see. So I'm going to continue. I'm going to assume that you paused the video already. And already try it out. So if I take the matrix... and I'm going to multiply by the direction vector, which have the same effect as if you plug in the vector into the variable. What you get will be this. You get, in this case, 2 minus 2 plus 0 plus 0. On the bottom, 0 plus 0 plus 0 plus 0. So what you get is actually 0, 0. That's interesting. Because that does not give me negative 2, 1, meaning that the direction vector does not satisfy our linear system, not like the position vector would do. But it does give me the 0 vector. Now that's interesting. Now is it just a coincidence that this one just so happened to give me a 0 vector? And in reality, the direction vector actually give you some random vector when you plug in the system? Well, let's find out what happened to a second direction vector. The second direction vector is negative 1, 0, 1, 1. So therefore, when I do a dot product, it will become negative 1 plus 0 plus 0 plus 1. On the bottom, 0 plus 0 plus 1 plus negative 1, or minus 1, I guess I could say. And that come out to be 0, 0 also. Now that is a result. I mean, if I only see it once, I can say it may be just by coincidence and come out to be the 0 vector. But now it happened both direction vector. Is that always the case? As a matter of fact, it is. See, the interesting thing about it is the following. For a linear system, let's say in this case, I'm going to call A vector x equal to B because I do need to somehow represent it. If the solution set is a k-planes in the form of let's say T1 vector U1 plus T2 vector U2 plus dot 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 plus T sub k vector U sub k plus vector V. The interesting thing about it is the position vector V, position vector V will satisfy the linear system A vector x equal to B. Or more precisely, it implies that if you multiply A by vector V, you will get vector B, which is what we show right here. Okay, if you let T1 equal 0, T2 equal 0, vector x would equal to vector V. And when you put that in by multiply by the coefficient matrix, you get whatever the equation equal to. Now, what happened is the following. What happened to a direction vector? The direction vectors, there are multiple of them. Will instead satisfy the following. Will satisfy what we call the homogeneous, actually I'm sorry, the associated homogeneous system, which is basically a vector x equal to 0 vector. So what does it mean? It implies that a times vector u1 is equal to a times vector u2 is equal to dot 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 equal to a times vector u sub k, and they all give you the 0 vector. Now, this unique property about the solution set of a linear system that happen to be in k-plane form give us something very powerful, and that will be this theorem, because it gives us the idea of what the solution to a linear system should look like and how it's structured. So theorem 2.2.4 is extremely important, especially for those of you who are in this class as a junior and planning to take differential equation next year. Because next year we're going to learn a similar theorems that pretty much say the exact same thing. Okay? And we're going to use that theorem to form the basis on how to solve any differential equation that we're going to learn next year. So that's how important it is. So if you understand this theorem now, it puts you in a significant advantage next year when we run into this. So what does this theorem 2.2.4 state? Theorem 2.2.4 states the following. Let's say given a linear system, given a linear system in the form of a vector x equal to vector b with an associated homogeneous system. So what is a associated homogeneous system? It's basically the same exact system, but instead equal to vector b equal to 0. Remember, homogeneous system or homogeneous equation means an equation that equal to 0. So in this case, it called associated homogeneous system because it uses the same exact coefficient matrix. That's the reason why. Then the solution set to the linear system a vector x equal to vector b is always in the form of vector x is equal to vector x sub h plus vector x sub p. So what are these two things? What is vector x sub h and vector x sub p? Vector x sub h is the solution set to the associated homogeneous system. So that's what the H stands for. Okay? A vector x equal to 0. And what is x vector x sub p? The letter p here stands for a particular solution. So what does vector x sub p is? X sub p is basically any one solution. It doesn't matter which one. Any one solution for the linear system. A vector x equal to b. So here's the interesting thing is, vector x sub h is the homogeneous solution, which you kind of have to solve for it. But vector x sub p can be just any one solution that you can come up with. You don't need to know every single one of them, just one solution that you can come up with. And you can then use that along with the homogeneous solution to come up with the entire solution set. And here, if you think about it, makes sense because remember, the solution set of a linear system, if it indeed have infinite solution, is a k-plane, but more importantly, in parametric representation. And what did we learn in chapter 1 about parametric representation? It is not unique. So therefore, there are a million trillion different ways to represent it. And in here, it illustrates that concept by allow you to use any one of the infinite solution to simply represent x sub p. And then combine that with the x sub h, it becomes your solution set. Therefore, it is important to understand is the following. Therefore, therefore, if the solution set of a linear system is a k-plane in the form of vector x equal to t1 vector u1 plus t2 vector u2 plus dot 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 plus t sub k vector uk plus vector v. Then this part right here where all the direction vectors are, along with all the perimeter, this is referred to vector x sub h. Just like what we illustrate in this example right here, that the two direction vector will give us the 0 vector when I plug in. So therefore, this part of the solution are just going to form the 0. Then what happened to the v right here? This v is vector x sub p. And this vector v can be any single one point in the entire solution set to help define what the solution is. Now, I do want to kind of show you the proof and then show you how to use this theorem. But unfortunately, this video is already 32 minutes. So I'm going to stop right here. And we're going to continue some more on the next video. Alright, talk to you guys later. Bye-bye.